from Hong Kong University of Science and Technology, and I'm supervised by Professor Chen. And today's report topic is a BIM-integrated indoor path planning framework for unmanned ground vehicle. And I have three parts. The first is about the introduction, and second part includes a proposed method and validation, and finally is conclusion and future work. First is introduction, and I'd like to tell about the background. And nowadays, construction matters for the world economy, but it has a low productivity, and its spending accounts for almost 30% of the world GDP, but its productivity growth has only increased 1% over the past 2 decades. And a lot of additional value added could be created through higher productivity. And robotics are considered as popular technologies to improve the productivity, and especially as UGVs, because compared with other robots, as they have larger payload, longer battery life, and safer movements. But they still have some limitations. The first is about the map generation. Traditional method like a SLAM, it is always time-consuming to fully cover the environment, and it is also lack of semantic information. Also, UGV's properties like the size and safety requirements are not always considered in the map generation step. So also another limitation on the path planning algorithm, because UGV's mobility systems are not fully considered. Some may fail in the indoor environments with limited space. So our objective is to propose an IFC-based method to integrate UGV's information and BIM models. And based on this model, we propose a layer mapping method. And then we also wanted to propose an improved A-star path planning algorithm that will be efficient in the indoor environments. And finally, we'd like to validate our proposed system in a physical engine-based simulation. And second is our method and validation. This is an overview of the framework. Firstly, we use IFC-based BIM and the UGV's models and the information as input. And then we do the integration in the first part. And based on this UGV integrated BIM, we can do the mapping. And in the third part, we improve the traditional A-star from 3 sides. And finally, we do the validation in a physical engine. And in the first part, we do the integration of BIM and robot information by the IFC scan. We use IFC building element proxy to define the UGV type. And we use IFC shape representation to save the geometric information, and like the zero face sets, zero color information. And in the third part, we use IFC property set to define the property sets and also their customized properties. So this is a customized IFC entity for UGVs. And a very important function of this step is we integrate different kind of files into the same format, and it will improve the interoperability. And this is a validation we realized in the Revit. In the second part, we based on the UGV integrated BIM, we can do the layer mapping, and we propose a IFC-based layer mapping. And this will have 2 advantages in vertical and there's a horizontal dimensions. So in the horizontal side, it will improve the data traceability because we can know the relationships between the IFC data and the map components. But while in the vertical part, we will know the mapping sequence, and we will know the inner relationships between among the map components. In the first layer, we will contain all the design building elements on the target floor, and in the second layer, we will update the information from the real world by IFC sensors. And in the final layer, we will construct the UGV-centric map for each UGV. Like we will consider their height, their safety buffer zones. And yeah, this is the second part. And we also validate this part in the physical engine. You can see we can increase obstacles like walls and ground in the first layer, and we can also realize a dynamic update for doors with sensors, and we can also add robots based safety buffer zones around the obstacles. In the third part, we improve the traditional A-star, and we propose an algorithm called adaptive A-star from 3 sides. The first is a primitive extension. We list the most common mobility systems for UGVs, and we further group them into two accounts. The first is unlimited UGVs, namely their motion directions and their body orientations are decoupled. So we just propose a primitive with straight and self-rotation ability. And for the second part, it is called limited UGVs because their motion directions are constrained to their body orientations because they have the fixed wheels. So we propose curved primitive for them. And for the second improvement, we just improve the traditional collision checking. And for the gaps of previous methods, always the objectives are considered as particles, and this will cause some problems in narrow corridors because when the length of UGVs are larger than is larger than the width of the corridors, and may consider infeasible. But however, it indeed exists feasible poles like when their width is smaller than the width of the corridors. And another problem is the waste of the space, because we know that the grasses are not always fully covered, and this kind of space is wasted. So this method may fail in narrow space, especially in indoor elements. So to fix this problem, we propose a three-step checking method. Namely, we will treat our obstacles and our UGVs as polygons, and we just check if they have intersections. And this is a cost to find process. We will first use a bounding box checking. It costs, but it is very speed up process. And then we do accurate checking, namely the line intersection checking, and the point in a rectangle checking. And in the final part, we improve the cost setting. We will not only consider the movement distance, but also the change of the body heading and change of the steering angles and their motion directions. And this also related to the efficiency of the energy of the UGVs. And in the validation part, we do the prototype modeling in the physical engine, and the geometrics can be imported from the BIM to the physical engine. And here we choose Unity in the FBX file, and the actual physical settings can also be added to our prototypes by Unity's building functions and also C# codes. And this is, we realize the path planning simulation for the UGVs. You can see it has a self-rotation ability, and it also has the parallel translation ability. And yeah, and we can also see the path searching process. And we also finished the path planning simulation for limited UGVs because they have, like I said, because they have constraints in their steering angles, so their primitive will be curved like this. And we can also see the search process and also the map information, whether it is occupied or not. And then we just list 5 metrics to validate our algorithms, namely the computation time, steering jerk, speed jerk, and this about the energy, and also the travel time and the success rate. And the final result shows our algorithm has good performance almost in every metric except the computation time. But it is not surprising because we indeed have a lot of extra calculations, but we think it is acceptable. And for the final conclusion and future work, for the discussion and the conclusion, we extend the traditional BIM to UGV integrated BIM, and this will improve the source management of construction-related robots, and it can also provide a knowledge base for robotic applications like the path planning and our work. And we also propose an improved A-star for UGVs because we consider the mobile systems into the path planning system, and we also the improved algorithm also shows good performance in both energy-related and efficiency-related matrix. And finally, the so condition speed is slightly affected. And for the future work, we will also test the robustness of the adaptive ISARC, like we will test them in the real world and in different environments. And thank you.